Hi, welcome back to another introduction to computer networks. This is Polly again, streaming live from NTU. All right, so let's check out the announcement today. This is week 14, and you know what? Hey, it does look like that we have fewer assignments due this Saturday. In fact, we do. PA9, I think many of the teams have already completed the submission. So we are just looking for maybe just 4 more teams, okay, to turn the PA9 in. Okay, so guys, so far so good. You're almost done with the PA assignments. This week we have 4 quizzes, and all these 4 quizzes are, well, not exactly trivial, and they are all about distance vector, okay, deriving the minimum cost and selecting the best neighbor to forward data. All right, and so all these PA9 and 4 quizzes will be due on Saturday. By the way, exam 2, okay, Polly just finished grading, but she needs a bit more time to organize the scores. And hi, Maria. And so, again, the results will be out at 1 p.m. tomorrow, very similar to exam 1. And Polly, do have a couple more things to announce today. Week 15, which is next week. Polly will be once again on conference travel. That means she will not be able to stream the lectures live. Okay. So similar to week 11, recall that there was a week earlier that Polly couldn't stream live, but you are assigned videos to watch and the quizzes to complete. So again, next week at the beginning, there's going to be an announcement called the W15 announcement. In that, you will see the list of videos to watch and the list of quizzes to complete. And then week 16, hey guys, week 16 is the final week, all right? There's not going to be lectures on Wednesday because I guess you guys will all be compressed, preparing or taking exams, okay, for the other classes you're taking. So on Wednesday, what Polly will do is I'll stand by on Discord and the Google Meet session. So feel free to drop by in case you have any questions you want to ask about the last exam we're going to have. Okay. So the last exam is, if you click into the exam 3 channel, you'll see the last exam is going to be on Thursday. And just like all the earlier exams in the morning. Now the exam scope, okay, in terms of the technical content, we'll cover chapter 4, 5, and a little bit of section 6 because this semester we turned out having a little bit more time for lecturing. So the scope is a little bit wider than the previous semesters, but it's not much, just section 6.1 to section 633. So that's the very basics of the link layer protocols. And for the exam, the scope of the PAs will actually span from PA3 to 9. So it's a little bit broader, but given the experiences from the earlier 2 exams, I think this is something that you are very familiar with. Okay, all right. All the rest will be very much similar to exam 1 and exam 2. All right. And now let's check out the topics today. All right, so today we'll finally talk about the distance vector algorithm. Last week we, of course, introduced the link state routing algorithm. It's essentially Dijkstra, okay, given the entire network's topology. You see that it might not scale in case the network topology grows really big. So you probably can't imagine link state running on the entire internet. That's why we have distance vector routing. Okay, and let me remind you of this quiz. Recall this one? Yeah, in quiz 41, you're asked to role play as a router. Recall? You're supposed to be a router X in particular, provided the information from the 2 neighbors. Okay, So router Y tells, hey, I know a way to the destination W and the overall cost is 3. Z says, over this way, over me, the overall cost is going to be 10. So you guys all did this, right? X being X, you check. If I go through Y, the overall cost is going to be what? 9 plus 3. And going through Z, 4 plus 10. And you pick the shorter overall path. Okay. That is exactly the spirit of distance vector. Okay, so next let me play this review video, okay, telling the spirit of distance vector. Very short, just 1 minute. That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hop that leads to the shortest path to the destination. And guys, you know what? That thing that you're doing as a router, going through all neighbors and find out what is the shortest, which neighbor provides the shortest overall route. That is called the Bellman-4 equation. So this is the next video coming up. And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So we define the term here. dxy is the cost, okay, of the shortest path to go from X to Y. And so what we're calculating here is the minimum cost to go from X to Y, or to discover the shortest path from X to Y. The way to do it is to go over all the V's. Okay, V's are the neighbors of the source. For each V, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor V. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from X to Y. And that V there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. Right? The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z. All right, so Bellman-4 equation. But you see, Bellman-4 equation is not the only thing in the distance vector algorithm. You see that before we could do the Bellman-4 equation computation, what do we need to know? We need to have the neighbors telling us what is the total cost to the destination, right? We call the DVW. Okay, so I forgot exactly who the destination node is. So we need to have these D something something, okay, from the neighbors. So the whole distance vector algorithm includes also a component that's collecting, okay, these distance vector reports from the neighbors. And after the router finished computing the Bellman-4 equation, it will get what? What is the best next hop and overall cost? So in case this is a better information, this router will need to what? Tell its neighbors, hey, this is good news. You guys might want to update your best route to a particular destination as well. So it might be now through me. Okay, so the whole distance vector routing algorithm is longer than just the Bellman-4 equation. And so this video a little bit long, about 6 minutes, but it's very crucial because the example is coming up and quiz 44 is coming up. So that was the Bellman-4 equation, which captures nicely how one discovered the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-4 is actually based on these information. Cij, okay, the link cost from the source to each of the neighbors, and these, the shortest distance from each of the neighbors to the final destination. All right. That is also saying the distance vector algorithm as a whole contains the Bellman-4 algorithm, but before the Bellman-4 can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. This actually relies on the neighbors, okay, sending their routing information to the node. Okay, so next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-4 part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Now, because this is the distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx, okay, for each node x, right? And before we could calculate dx, okay, the node here needs to have two pieces of information. Okay, according to the Bellman-4 equation, we need to know the link cost from the node to each of the neighbors. So CXVs. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know, okay, the neighbors' distance vectors. So for each V, node X here also maintain DV. And now the algorithm of distance vector routing. You see here, okay, key idea is it works in two phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then two. When the node receives the distance vectors from all the neighbors, Bellman-4 equation calculation begins. And as a result, okay, the no x there discover its own distance vector. And we could loop back. Okay, this no here then will pass the dx to the neighbors. Okay, that is the general idea of distance vector routing algorithm. The Bellman-4 equation, now this is the Bellman-4 equation. Okay, know that when x receives all these dv's from the neighbors, okay, dx is not just one value to one particular destination. So this Bellman-4 equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, n. All right. Yeah, final note here. Under minor natural condition, yeah, the shortest distance from x to y, at the beginning, it might be really, really bad, okay? But as time goes by, it's going to converge to the actual least cost. So minor natural conditions means that, yeah, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network, okay, operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Okay. Occasionally, this router here might detect there's a link cost change, okay, among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. Yeah, so when these two events occur, yeah, we trigger Bellman-4 calculation to begin. Okay. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, okay, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit, okay, from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, okay, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. Okay. It's also distributed because one can calculate and discover a better route and pass it to another node. Okay, so each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network. All right, so that's the whole distance vector algorithm. So we'll start with an example, but let me explain a little bit more, because as you heard in the video, the way distance vector works is iterative, of course, and it's asynchronous. So each node will be taking vectors from others and then do the Bellman-4 computation somewhat independently. Okay, so the nodes, when they're doing the computation, it might not be exactly synchronized. Okay, but for the rest of the lectures, in order to be able to do computations at all, for all these examples that you will see in the lectures as well as in the exams, okay, we assume the nodes, okay, will be sending the distance vectors, these reports, in a synchronous fashion. Okay, otherwise it's just really hard to do any computation, right? Okay, yeah, but it seems that the volume of the recorded video is low. Does anyone has the same problem? I see, so it might be a little bit low. I will try to adjust, okay, the volume to something that's a little bit higher, okay, but hopefully not overly high. Okay, we'll see. So in the next video, you will see Polly illustrate distance vector. Yeah, thank you for the feedback. I'll raise the volume a little bit. But in the video, you will see there's also an initialization phase. Each node at the beginning will actually try to set the initial distance vector, because at that time, there are no information from the neighbors yet. Okay. So then the live lectures. Started using Firefox extension, okay. I see. Yeah, so certain browsers allow you to tune the volume a little bit flexibly. All right, so let me play this video, and hopefully I adjust the video in a way that it will be a little bit more audible. Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. example this time, very simple, only 3 nodes, x, y, z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. In node x, okay, the distance vector of x is initialized this way. For destination x, well, it's itself, therefore, distance 0, it does not cost anything, okay, to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So 2 here. xz, so xz, they're adjacent, therefore we use the link cost between xz. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, hey, in node x, it maintains all neighbors' distance vector, alright, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. Okay, so I'm just using the sign of infinity there, okay, to represent their null. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table, which is composed of 3 vectors. Okay. You maintain your own vector, you maintain also the neighbor's vector. Now, once, okay, the vectors are initialized, each router will what? Okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, x to all the neighbors, y and z. Similarly, node y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, node x here in the table, it's going to see dy from node y, dz here from node z. All right. Now, with neighbors distance vector in place, now we can begin to calculate the dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors, okay, of the source. X is right here, the source. 2 neighbors, y and z. So yeah, we do have 2 entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0, okay, as dy y says 0. Link cost xy, 2, so 2 here. Now, for the second neighbor, z, link cost of xz, 7, so 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y, right here, it says 1. So 7 plus 1, this is 8, and this is 2 only. Therefore, y here wins. Okay, y is the next hop router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz, okay, so from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's gonna what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy. No z there is going to be calculating the dz because it's receiving dx and dy. Polly talking. Polly talking. Can you guys hear me now? Ah, there we go, finally. Yeah, sorry for the glitch. Because I was trying to pause that last video, the very last part of it, so that Sylvain can see. Okay, when these distance vectors finally converge to the optimum routes, yes, the cost from xy should equal the cost from y to x. But you see, in the middle of deriving it until you really converge to the best results, you see in that table at x, xz was 3, but zx was 7. Okay, so each row there represents a router's perception of the best routes to the destinations. So z's perception of the best routes to x is not quite x's perception as best routes to z. So x at that point knows a little bit better, okay, than z. All right. So, oops, sorry. Yeah. So I messed up my stream deck a little bit. Sorry, guys. Let's see if I can come back. Okay. So essentially, what's coming up is quiz 44. Polly just derived the table for no x, okay, at the first iteration after initialization. So what about you guys deriving the table at no z at the first iteration? Okay. So you see here, this was the table we ended up having, right? xz was 3 and zx was 7. Okay, great. Thank you. Thank you for letting me know. And sorry about the glitch. And you guys are asked to calculate dz at this time point. And so this is after what? X sends 0 to 7, y sends 201 to z. And z, upon receiving these information from the neighbors, can begin to apply the Bellman-4 equation. All right. So this is quiz 44. But be careful. For this quiz, we are not looking for fast responders. Okay, so I'll be taking those with the detailed derivation. Okay, the most detailed derivation will get the bonus. Right. So this is also for you to exercise Bellman-4 equation. Okay, you see that distance vector is just not that intuitive. It's a very sort of low intelligence routing. Okay, so we just don't know the global information. But if you look at the topology, you see the total information. So as human beings, it's not that easy for you to do the derivation. Okay, so now let's go to the discourse space. Okay, channel W14, quiz 14. So you guys have 8 minutes. So this is the longest tolerance time for the quiz. The point is for you to exercise. For some of you, it might be easier if you take, if you derive on your notebook, take a picture of that and upload the picture. Okay, so in case typing up symbols and stuff like that, make it slow. So now let's start counting time. 8 minutes. Derive dzx and dzy. Oh, I see actually Team 4 already type up something. But hey guys, no worries. I take the detailed derivation. So 8 minutes, let's work on this. Yeah, I guess Zhenyu, you probably discovered the issue here. Because we're calculating dzx, right? Then you take the link cost from z to the first neighbor x. Okay, and link cost from z to the second neighbor y. But I see that you get the idea, so probably just misplacing the first character here. All right, and the second is to compare. I think this is z to y. And this is z. Should be z to x, z to y, or something like that. If I Yeah, I think Zhenyu, you might want to check on your equations a little bit more. From z to x, from z to y to the second neighbor, z to x, and then the second neighbor. And so this is the cost from x to x. This is the cost from y to x. And this is to calculate for destination y. Okay. Great. Yeah, so I see XX and YY are of course 0. So team 2's derivation, the second term is omitted because the value is 0. Okay, good. All right. So Maria is turning in an uploaded version of it. XZ, ZX, ZY, okay. Sorry, I need to blow it up to make sure that I see. So I think Maria, are you deriving CX? Oh, okay, okay. Yeah, yours is good. Great. It's just a little small, a little bit challenging for Polly's eyesight. Sorry. Okay, let's see. Looks good to me. All right. All right. Great. So happy to know that I think you guys are getting this. Okay. So distance vector routing is just not that trivial. It in the intermediate steps, you just have to follow. You just have to follow the Bellman-Ford equation, and play dumb like a distance vector router. And there's in our previous image. Oh, really? Okay, okay. So I'll then accept this as well. Okay. Yeah. So guys, you get the idea. So it's a little bit tricky, trickier than usual. So next is probably playing the video deriving Z's table as well as Y's table. How about that? So then we complete iterating the T1. Let's try to calculate the distance vector of Z together. So you see, it will be the shortest distance from Z to every possible destination in the network. And in the network, it's very small. Starting from Z, there are only two possible destinations, X and Y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Bellman-Ford equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination X. Now, in this network, we do have two neighbors, okay, connected to Z. So let's try the first neighbor first, which is Z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, Z to X being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is X, destination is also X. Now we look up the table. So dx here being known to Z, according to that, the XX is 0. Now the second entry, the second neighbor is Y. Okay, so we'll then take link cost from Z to Y, which is 1, and then based on Y knows the best to the destination X. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wins. Okay, so you see here, to go from z to x, the shortest path distance is 3. And the next hop is obviously y. Well, let's calculate the other entry, which is zy. Let me clear the markup first. All right. Okay. Again, according to the Bellman-Ford equation, source is z, and the destination we wish to find out the shortest path causes is y. Yeah. In the Bellman-Ford, we'll try, right, for two different neighbors in this network of z and c, which lead us to the shortest path. So let's try the first neighbor here, x, link cost being 7 again, and then, what about dxy? Now let's look up the table. It's dxy, therefore, yeah, the shortest distance is 2. So we ended up adding 7 to 2, which is 9. That doesn't look so good. What about the other neighbor of z? zy is 1 again. What about the shortest distance from y to y? And hey, it's itself, so y to y, the cost is 0. So okay, this other path going through y give us only path cost 1, therefore, yeah, going through y, this gives us the shortest path from z to y. And therefore, we update the entire dv, which is now 310. We can actually continue and calculate what is dy, isn't it? So there are again two entries, yx and yz. Let's calculate yx first. Okay, this time y is the source and destination is x. Again, we need to try through all the neighbors of y. So let's start from x. Okay, so x in the middle, source being y, destination being x. So we go through link yx, which is 2 here, and then find out what is the shortest distance from neighbor x to the destination x. So neighbor and destination happen to be the same node. According to the table, x, yeah, the value is 0. So here, going through neighbor x, ooh, nice, total cost is 2. The other neighbor, so y's other neighbor is what? Z. So z in the middle here. Link cost yz, 1. What about the shortest distance z knows to the destination x? So dzx, we'll have to look up the table here. dzx, which says 7. So the best path, okay, going through neighbor z is unfortunately, yeah, costing us 8. So comparing the two, yeah, the path going through neighbor x is better. Okay, so yx and then reaching x. So total cost 2. So we can now update, yeah, dyx to 2. The second entry in the distance vector of y is dyz. Okay, so again, starting from y, going to the final destination z. So starting from y, and this time final destination z. We'll have to try through both neighbors. First neighbor being x, link cost from y to neighbor x is 2. The shortest distance from x to the final destination z, oh, dxz. So let's see, dxz. Yeah, the entry in the table says 7. Second neighbor being z here, so yz, the link cost is 1. Nice. What about the shortest path from z to the final destination z? Yeah, it's actually quite straightforward, isn't it? zz, trivially 0. And 9 comparing to 1, which one is shorter? 1 here. At this point, we can also update the entry dyz. And this is how we come to the distance vector of y. So we now finish deriving all the distance vector tables at time t1. What you see also is this. Look at this. dy and dy, okay? Between t0 and t1, dy did not change. Therefore, dy here, no y here, does not need to propagate the data, okay? Propagate the vector to no x and no z. While, okay, when x here finds out the dx, which is different, okay, from t0's dx, we need to propagate dx to no y as well as no z to calculate the table for t2. Similarly here, z find out the new dz being different from the old dz, we need to propagate also. okay, dz to no x and no y. Therefore, the two other nodes can calculate if the dx and dy needs to be changed further. All right, so that's after T1. All right, so the last video today, about 1.5 minutes, that's go on and derive for T2 and C if these distance vector tables converge, meaning none of these nodes x, y, z after T2 will need to send the vector further. You see that in this after T1, y doesn't need to send the vector further because it's already the optimum. Okay, so last video. So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. Okay. So no x receiving the update is going to replace this with a new distance vector. Right. Just like y here, okay, this vector here is going to be also replaced with a new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 027 to 023. Now, what's a bit special is this, okay? In the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. Okay. So this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz, therefore this gets changed to 023, this gets changed to 310. You see that in cycle number 2, x, y, and z, they actually converge. Okay? The view is consistent and they all converge to the shortest path, okay? The least cost path. So in this very simple example, we see distance vector using the Bellman-4 equation works really well, converges in 2 cycles. All right, so that's distance vector routing. You see that after we all converge to the shortest route, yes, the cost from x to y versus the cost from y to x, they are equal. Okay, so you will see that the table look symmetric. Okay, over the diagonal. Now, next topic is called bad news travel slow. So this is a very, very special property of distance vector routing. But you know what? We won't have time to go over this property today. So what we will do first thing tomorrow morning is to introduce this property through a couple examples. So bad news travel slow, but good thing is that good news travel fast. So in case the network is changed such that certain cost of a link is reduced, which is a good thing. Then good news actually travel really fast. We converge fast using distance vector. But in case the link cost goes longer, okay, higher, then that's bad news for the network. That okay is quite a headache. Okay, tomorrow through quiz 45 to 47. We'll again iterate through stages of doing the distance vector computation for a network, and you will see that it will take a long time finally for the network to converge the new best routes. All right, with that said, I say goodbye. Yeah, that's all the time we have, and I see you tomorrow. Bye.